Hello. In this video, we're going to be taking a look at testing claims about standard deviations. The notation: n is your sample size, s is the sample standard deviation, s squared the sample variance, sigma the population standard deviation, sigma squared the population variance. The requirements is that it has to be a simple random sample, and also the population needs to have a normal distribution. Our test statistic is chi-squared, and it's equal to n minus 1 times s squared over sigma squared. What you will need to show for each hypothesis test: the statement of the null and the alternative, a graph showing the appropriate distribution, the test statistic, and either the p-value or the critical values and critical region. A statement of either reject the null or fail to reject the null, and then your conclusion statement. Example 1, dataset 19 in Appendix B includes volumes in ounces of a simple random sample of 36 cans of regular Pepsi. Those volumes have a mean of 12.29 ounces and a standard deviation of 0.09 ounces. They appear to be from a normally distributed population. If we want the filling process to work so that almost all cans have volumes between 11.8 ounces and 12.4 ounces, the range rule of thumb can be used to estimate the standard deviation should be less than 0.15 ounces. Use the sample data to test the claim that the population of volumes has a standard deviation less than 0.15 ounces. Use a 0.05 significance level. The first thing that we need to do is write down our claim and the opposite. The claim is that the standard deviation is less than 0.15 ounces. The opposite then would be that sigma is greater than or equal to 0.15 ounces. The null hypothesis is sigma equals 0.15 ounces, and the alternative is sigma is less than 0.15 ounces, and the alternative is our claim. The significance level of the test is 0.05, and the degrees of freedom is n minus 1, so for this one that would be 35. Now calculate the chi-squared statistic. That's n minus 1 times s squared over sigma squared. N minus 1 is 35. Our sample standard deviation s is 0.09. And our population standard deviation is 0.15. This should give you 12.6. Next, if you're going to use your calculators, your graphing calculators, to find a p-value, in order to do that, you would need to click on second bars, and then select the chi-squared CDF. There is no test for standard deviations in your graphing calculator, so you'll just need to use your calculator to find the p-value. You'll have to give it the lower bound, the upper bound, and the degrees of freedom. So entering this information into your calculator, you would get 1.79 e negative 4. So that's 0.000179. And this number is less than our significance level of 0.05, which tells us that we would reject the null. Now to find the critical value. For this one, we're using a significance level of 0.05. It's a left-tailed test, so the area in the left tail is going to be 0.05. Now remember, the chi-squared distribution is not symmetric. and the table gives us areas to the right. Since the area in the left tail is 0.05, the area in the right tail would be 0.95. So here is the chi-squared table. Along the top, we want to find the 0.95 column because that's the one that has an area to the left of 0.05. Remember, this is the area to the right. And so we're going to be using the fourth column over. We have 35 degrees of freedom. Unfortunately, that's halfway between 30 and 40, so we're going to use the average of these two. So that is the average of 18.493 and 26.509. And the average of those two numbers is 22.501. So now draw your graph. Remember, this is not symmetric. It goes from 0 up to positive infinity. Our critical value is 22.501. You could even use the lower one if you wanted to, because our test statistic is even smaller than that. So this is our critical value. Our test statistic chi-squared is 12.6, and since our test statistic is in the tail, we are going to reject the null. And then to make a little graph for the p-value way, so our p-value is 0.000179, and alpha is 0.05. And so our alpha level is bigger than our p-value, or another way to say that is that our p-value is smaller than our alpha level, so we're rejecting our null, and then we need to make our conclusion. Here, the claim is in the alternative. We are rejecting our null hypothesis, so quote unquote we're accepting our alternative. So that means there is sufficient evidence to support the claim that the standard deviation is less than 0.15 ounces. Example 2. A simple random sample of 40 women results in a standard deviation of 11.6 beats per minute based on data set 1 in Appendix B. The normal range of pulse rates of adults is typically given as 60 to 100 beats per minute. If the range rule of thumb is applied to the normal range, the result is a standard deviation of 10 beats per minute. Use the sample results with the 0.05 significance level to test the claim that the pulse rates of women have a standard deviation equal to 10 beats per minute. Our claim and our opposite. The claim is that the standard deviation is equal to 10 beats per minute, so our opposite would be that the standard deviation is not equal to 10 beats per minute. The null and the alternative. The null is that the standard deviation is equal to 10 beats per minute, and the alternative is that the standard deviation is not equal to 10 beats per minute. Our significance level is 0.05, and our degrees of freedom is equal to 39. Next, we need to calculate our chi-squared statistic. So that's n minus 1 times s squared over sigma squared. N minus 1 is 39. S is 11.6, our sample standard deviation, and we want to square that, divided by our population standard deviation, which is 10, and then square that. When you calculate this, you should get 52.478. If you want to use your calculator to find a p-value, here we have a two-tailed test, and so we have to remember to multiply whatever we get in our calculator by 2. And for this, you're going to want to enter in 52.478. And then 9,999 and 39 for your degrees of freedom. When you put this in your calculator, you should get 0.07317. Multiply that by 2, we get 0.1463. This is greater than alpha, 0.05, and because it's greater than alpha, we're going to fail to reject the null. We can draw our graph. It's a two-tailed test, so half of alpha would be 0.025 in this tail and half in this tail. So the weird thing about doing the graph with a two-tailed is that then you really need to take the number before you multiplied by 2, and that was 0.07317, and then put it over here as well. And over here, if you are not going to be using a graphing calculator, then we need to find our critical value. Our alpha level is 0.05. Because it's a two-tailed test, we need to divide that by 2. And 0.05 divided by 2 is 0.025. So we need to find two numbers in our table. The first one is going to be with an area to the right. That's going to be 0.975. And then also the area to the right, that's 0.025. So let's bring up our table. So we want the 0.975 area to the right. That's going to be the tail on the left with an area of 0.025 to the left of it. And we have 39 degrees of freedom. The number in the table that's going to be closest to that would be the 40 degrees of freedom. And so we would use that number. So that's 24.433. So that's one of our critical values. The other critical value is going to be this one with the 0.025. So that's the area to the right. And so when we go down to 40 degrees of freedom for that one, we find that our value is 59.342. So our two critical values are 24.433 and 59.342. Make your graph, and our critical value here is 24.433. Critical value on this end is 59.342. And then put your test statistic on there, and our test statistic chi-squared is 52.478. This is not in one of the tails, and so we're going to fail to reject, just like the decision that we make with our p-value. Now we need to make our conclusion. We are failing to reject the null, and the claim is in the null. So that makes our conclusion there is not sufficient evidence to reject the claim that the standard deviation is equal to 10 beats per minute. For our last example, a simple random sample of the heights of 10 supermodels with a mean of 69.825 inches and a standard deviation of 0.7997 inches tests the claim that the supermodels have heights that have much less variation than heights of women in the general population. We will use a 0.01 significance level to test the claim that supermodels have heights with a standard deviation that is less than 2.6 inches for the population of women. The claim is that the standard deviation is less than 2.6 The opposite is that the standard deviation is greater than or equal to 2.6. Our null, that's always the equal to statement, so the standard deviation is equal to 2.6, and the alternative is our claim that the standard deviation is less than 2.6. Our significance level is 0.01, and our degrees of freedom is 9. The test statistic chi-squared is n minus 1 s squared over sigma squared. So that will be 9 times 0.7997 squared over 2.6 squared. This should give you a value of 0.851. The p-value, using your calculator, you should get 2.89 e negative 4. This is less than our significance level of 0.01, and so we are going to reject the null. Drawing out a picture of that. This is a left-tailed test. Our significance level alpha is 0.01, and our p-value is 0.000289. If you don't have a graphing calculator and you're going to look up your critical value, this is a left-tailed test. So, and our significance level is 0.01. That means, so you need to subtract that from 1, because this is the area to the left. We want the area to the right when we look it up in our table. So we are going to use the column for 0.99, and we had 9 degrees of freedom, so our critical value is 2.088. Draw a picture. We have our critical value of 2.088, and our test statistic, chi-squared, was 0.851. Our test statistic is in the tail, and so we will have the same conclusion that we're going to reject the null hypothesis. We're rejecting the null hypothesis, which quote-unquote means that we're accepting the alternative, and that is where our claim is, and so we do have sufficient evidence to support our claim. that the heights of supermodels varies less than the heights of the women in the general population. So that's it for this video. Let me know if you have any questions, and I hope you're having a great day.